In this video, we're going to take a look at the double angle formulas and solve some problems involving those. These are identities for the functions sine of 2 theta, cosine of 2 theta, and tan 2 theta. Let's firstly go ahead and verify these identities. Previously in this series, we have looked at the sum and difference formulas. We derived these formulas geometrically. And now that we have these identities, verifying these double angle identities is pretty straightforward. Maybe you can see the connection between sine of 2 theta and this identity here, sine of A plus B. So let's go ahead and start with sine of 2 theta. We can write that as sine of theta plus theta. And then we can use the sum formula for the sine function to say this would be sine of theta cosine of theta plus sine of theta cosine of theta. Here I'm just using the fact that sine of A plus B is sine of A cosine of B plus sine of B cosine of A. Because we have theta plus theta, this is what we get. And then we have two lots of sine theta cosine theta. So that's the first identity there. Let's go ahead and do cosine of 2 theta. Again, we can write this as cosine of theta plus theta. And using this identity, this is going to be cosine of theta, subtract sine of theta, sine of theta, which is cosine squared theta, take sine squared theta. Okay, that's the first one. For the next one, you need to remember that sine squared theta plus cosine squared theta equals 1. And you can rearrange this to say that cosine squared theta equals 1 take sine squared theta, and also sine squared theta equals 1 take cosine squared theta, and use these to substitute into this expression. So this was our first identity, and then we can substitute in, for example, 1 take sine squared theta for cosine squared. This would be 1 take sine squared theta take sine squared theta, which is 1 take 2 sine squared theta. That's our next identity there. And if we take this expression again and substitute in 1 take cosine squared for sine squared, this would be cosine squared theta subtract 1 take cosine squared theta. And then this is cosine squared plus cosine squared, which is 2 cosine squared theta, take 1, and that's our last identity. So in that example, we have 3 identities we need to be aware of. And the last one is tan 2 theta. Let me just move this up a little bit. Tan 2 theta. This is tan of theta plus theta. Using the sum formula for the tan function, this is tan of A plus tan of B. So tan of theta plus tan of theta over 1 take tan theta, which is 2 tan theta over 1 take tan squared theta. So pretty straightforward to verify those identities once you have the sum and difference formulas. Let's go on and have a look at some example problems now involving these. And also this is going to involve all of the other identities we've looked at in this series as well. So the first problem we can do is going to be tan 2 theta is equivalent to 2 on cotangent theta take tan theta. And these are all going to be show that questions. So we're verifying trigonometric identities. You want to show that the left-hand side is equivalent to the right-hand side. Okay, so we could either start with the right or the left. I'm going to start with the left-hand side. So tan of 2 theta, we have just shown that tan of 2 theta is 2 tan theta over 1 take tan squared theta. Now when verifying trig identities, you need to be aware of some of the tricks you can use. So in this example, we can divide the numerator and denominator by tan theta. So this will be 2 tan theta divided by tan theta in the numerator, and in the denominator this will be 1 on tan theta take tan squared theta on tan theta. And then in the numerator, we're just left with 2. 1 on tan theta is cotangent theta, and tan squared theta on tan theta is tan theta. And there we have the right hand side. So that's a pretty common trick you can use in these types of problems. The next example is 1 take cosine 2 theta over sine 2 theta is equivalent to tan theta. Okay, let's start with the left hand side again. 1 take cosine of 2 theta, we want to use the identity there. Now you have to decide which one you might want to use. So try to think ahead a little bit. If we're trying to end up with tan theta, that probably means we want a sine theta in the numerator. So one way to get a sine theta in this numerator is to exchange 1 take 2 sine squared theta for cosine 2 theta. So my first step will be to substitute in this identity. That's 2 sine squared theta. And in the denominator, also use that identity for sine 2 theta, which was 2 sine theta cosine theta. Expand these brackets out. 1 take 1 is 0. Negative 2 sine squared theta is just 2 sine squared theta on 2 sine theta cosine theta. And then you can do some cancelling. The 2's will cancel. The sine in the denominator will cancel with one of the signs in the numerator, and we're just left with sine theta over cosine theta, which is the right hand side. The next example, example 3, we have sec squared theta over 1 take tan squared theta is equivalent to sec 2 theta. Let's start with the left hand side. Sec squared theta, I'm going to leave as is for now, but you need to remember that sec theta is 1 over cosine theta, so this would be 1 over cosine squared theta. In the denominator, I'm going to write that as 1 take sine squared theta over cosine squared theta, and then combine these two terms. So the common denominator will be cosine squared. So I'm going to write that as sec squared theta over cosine squared theta take sine squared theta over cosine squared theta. And actually now we could change this sec squared into 1 over cosine squared theta. And whenever you have a fraction divided by another fraction and they have the same denominator, you can just cancel that out. Hopefully you're aware of that. You know, you can go through the whole process of flipping and multiplying, but that's what happens. You cancel those two denominators, and we're just left with 1 over cosine squared theta take sine squared theta, which we know is 1 over cosine 2 theta. That's that identity for cosine 2 theta, which is sec 2 theta, which is the right hand side. Okay, next example, sec theta take 1 over sec theta plus 1 is equivalent to tan squared theta on 2. Again, starting with the left hand side, we could write this as 1 over cosine theta take 1 over 1 over cosine theta take 1. And combining these terms, we're going to have 1 take cosine theta over cosine theta all over 1 take cosine theta over, sorry, that's meant to be a plus 1 plus cosine theta over cosine theta. Again, we have that common denominator in the numerator and denominator. They can cancel out, and we're just left with 1 take cosine theta over 1 plus cosine theta. In this expression, we just have cosine theta, but you can still use the double angle formula. Just because it's not cosine 2 theta, it doesn't mean you can't use the double angle formula. That's really messy. I don't know why. If it's just cosine theta, you can say this is, for example, 1 take sine 2 sine squared of theta on 2. So all you do is divide that angle by 2, and you can still use these identities. So that's what we're going to do here, substituting in 1 take sine squared theta on 2 for this cosine theta in the numerator. So 1 take sine squared theta on 2. And in the denominator, we're going to use the other identity, which was 2 cosine squared theta on 2 take 1. So in the denominator, we have 2 cosine squared theta on 2 take 1. Here we have 1 take 1 in the numerator, which is 0. So we're just left with sine squared theta on 2. In the denominator, 1 take 1 again is 0. And I forgot the 2 there. So that should be 2 sine squared theta. And then in the denominator, we have 2 cosine squared theta on 2. The 2's cancel, and we're just left with tan squared theta on 2, which is the right-hand side. So there you go. That was that example. Let's have a look at a few more. We're also going to be using the sum and difference formulas. So in this example, we've got tan of pi on 4 subtract x is equivalent to 1 take sine 2x over cosine 2x. Starting with the left-hand side, this would be tan of the first angle, so tan of pi on 4, subtract tan of the second angle, tan of x, over 1 plus the tan of pi on 4 multiplied by the tan of x. The tan of pi on 4 you should know is 1. Think back to your exact values of trig functions. So in the numerator, we've got 1 take tan of x. And in the denominator, this would be 1, so we've got 1 plus tan of x. Now, did this expression come up previously? No, not quite. So anyways, we can write this now as 1 take sine x over cosine x. And this is divided by 1 plus sine of x, cosine of x. And then combine these terms like we were doing previously. This would be cosine of x take sine of x over cosine of x. I'm going to skip a step here because I already know I'm going to cancel out that denominator of cosine x. So I can just write this as cosine of x take sine of x over cosine of x plus sine of x. And then here I'm going to use another little trick that you need to be aware of that is often useful when verifying trig identities. You can multiply by something in order to get the expressions that you want. So here I'm going to multiply by cosine of x take sine of x over itself. So that's just multiplying by 1. Why would I do this? Well, you notice in the denominator now I have cosine of x plus sine of x multiplied by cosine of x take sine of x. That's going to be the difference of two squares, which I know is going to end up to be cosine of 2x. So that's how you might find that you need to take this step, by looking at what you need to end up with and figuring out how to end up with those identities that you need. So if we expand out these brackets then, in the numerator, we're going to have cosine squared x take sine x cosine x take well, that's going to be 2 lots of sine x cosine x, and then subtract, or plus, sorry, sine squared x. In the denominator, as I said, we have the difference of two squares, so this is cosine squared x take sine squared x, and then we have cosine squared x plus sine squared x in the numerator. That's just 1, so that's going to be 1 take 2 sine x cosine x. That's the double angle identity for the sine function, so that's sine of 2x. And in the denominator, this was cosine of 2x, which is the right hand side. And we're done for that example. Just a couple more I wanted to look at. So in this example, we have sine squared of 45 plus theta plus sine squared of 45 take theta, and that's equivalent to 1. When you have this situation where you have a compound angle and the function is squared, don't make the mistake of just using the sum formula. So for example, sine squared 45 cosine squared theta plus, etc. This is not equivalent. So you need to think of this as sine of 45 plus theta all squared. Then you can use the identity to expand out that function and then square it. So you can see there's going to be a fair bit of work involved here. So on the left hand side, start with that. As I said, I'm going to think of this as sine of 45 plus theta all squared, and then this one's going to be sine of 45 take theta all squared. So use that identity for the sum of the angles. This is going to be sine of 45 cosine theta plus sine of theta cosine 45 squared plus sine 45 cosine theta subtract sine theta cosine 45 squared. Then remember what sine of 45 and cosine of 45 are. That's 1 on root 2 or root 2 on 2. So let's use root 2 on 2 cosine theta, and the same for cosine 45 is root 2 on 2 sine theta all squared, and same over here, root 2 on 2 cosine theta take root 2 on 2 sine theta all squared. And now we need to expand out these brackets. So if you imagine these are double brackets, we're going to multiply this by itself. So this is going to be root 2 on 2 squared is going to be 2 on 4, which is a half. So a half cosine squared theta plus 2 lots of these things multiplied together. So let's write that as 2 times 2 on 4, because root 2 on 2 times root 2 on 2 would be 2 on 4. And of course we can simplify this. I'm just going to do that in the next step. So I'm showing more of my working out. And then this would be sine theta cosine theta. So 2 lots of this. And then on the end we have plus a half sine squared theta. Okay, I'm going to run out of room here. So let's go on to the next line. Then we have plus essentially the same thing. This is just going to be a negative in here. So a half cosine squared theta subtract this. So let's simplify that now. That would be what? A half times 2, which is 1. So subtract sine theta cosine theta. And then plus a half sine squared theta. So this will be plus sine theta cosine theta take sine theta cosine theta. They are going to cancel each other out. And then we have a half cosine theta plus a half cosine theta, which is 1 lot of cosine squared theta. And then the same thing for the sine squareds. So this cosine squared theta plus sine squared theta is 1, which is the right hand side. The final example I wanted to look at was cosine of 3 theta. And we need to show this is equivalent to cosine cubed theta take 3 sine squared theta cosine theta. Let's start with the left hand side. Cosine 3 theta we can think of as cosine of 2 theta plus theta. Expanding this out, this would be cosine 2 theta cosine theta subtract sine 2 theta sine theta. And now we want to substitute something in for cosine 2 theta and sine 2 theta. So which identity to use for cosine 2 theta? Well, because we end up with a cosine cubed, that leads me to believe that I want to use the cosine squared theta take sine squared theta identity. So substituting that in for cosine 2 theta, and then sine 2 theta is 2 sine theta cosine theta times sine theta. Simplifying this, expanding these brackets, this is cosine cubed theta subtract sine squared theta cosine theta take 2 sine squared theta cosine theta, and these are like terms, so combining those we end up with cosine cubed theta subtract 3 sine squared theta cosine theta. So just a few examples there. I highlighted those because there were some little tricks we used in there involving these identities. The first one was, you can often divide the numerator and denominator by some function to simplify it to the identity you want to end up with. The other thing is that because we have those three identities for cosine 2 theta, often you have to think strategically about which one you want to use. So look at what you're trying to end up with and let that help you decide which of these identities to use. And the other thing we talked about was multiplying, by something. In this example, we use cosine x takes sine x over itself in order to end up with the final answer. So a couple of little tips and tricks there. Well, they're not really tricks. I don't know what to call them really, but little problem solving strategies you can use when you're verifying these identities. Hope you found that useful. Please leave a like if you did, subscribe if you want to see more content, and I'll see you in the next one. Bye for now.